have mentioned that the power electronic circuits in which only diodes are used as switches can be classified under the category of rectifiers, as they can perform AC to DC conversion. In addition to diodes, we can also have inductors and capacitors in these circuits. So in the first circuit, the power electronic converter contains only diode as switch and no other element. In the second circuit, there is diode and inductor. In the third circuit, there is diode and capacitor. And in the fourth circuit, shown here, there are a couple of diodes and an inductor. In all these four circuits, the input voltage Vs of t is a sinusoidally varying voltage, and the output voltage Vo is a DC voltage. And what do we mean by DC here? By the notion of DC that we introduced, Vo is a time varying voltage with finite average value. It is not a constant voltage. The four rectifier circuits that are shown here come under the class of 1-pulse diode rectifiers, or they are known as single phase half wave rectifiers. And this 1 pulse refers to the pulse number being 1. Pulse number is a very popular measure used for rectifiers. It is used to describe the nature of the output voltage waveform of a rectifier. It refers to the number of input voltage pulses appearing in one cycle of the output voltage. It can be formally defined as time period of input voltage divided by the time period of minimum order harmonic in output voltage. We will get to know more about pulse number as we proceed. We will be looking at another special case of load known as RLE type of load. And what does this signify? It signifies a DC motor. If we are connecting a DC motor at the output of rectifier, it is equivalent to an RLE load. And what is E? E is the back EMF of a DC motor, which is the induced voltage in armature winding, and it is proportional to the speed of the motor. R and L refer to the resistance and inductance of the armature winding. And why are we defining inductance here in a DC circuit? Even though it's a DC circuit, there is a time varying current. The currents are varying with time. So whenever there is a time varying current, there is a time varying flux, and the current can be associated with the flux linkage using an inductance. So we'll be learning about all these 1-pulse diode rectifiers. And what is the method of analysis? It is the same as that described before. First, we try to determine the state of the diode, whether it is on or off, and in each state we apply KCL, KVL to determine the physical quantities, voltages and currents of interest. And we'll also apply the principles of periodic steady state to arrive at the waveform measures, volt second balance or charge balance that can be applied. Let us proceed with the analysis of the first circuit, which is a single phase half wave rectifier with a resistor as load. The circuit is shown here. We need to determine the state of the diode to start with. Let us assume that before t equal to 0, that means before this point, the diode is off, nothing is happening in the circuit. And at t equal to 0, the voltage Vs becomes positive, so which is Vs greater than 0. And let us assume that the diode continues to be off. If the diode continues to be off, what do we infer from its properties? The voltage across the diode should be less than 0. That inference is given in, it's written in green color here. The VD1 should be less than 0. Since we have assumed that the diode is off, we should look at its voltage and verify that it is consistent with the inference, or it is consistent with the property of the diode. So let us try to determine the voltage across the diode. And how do we determine? We first need to define the polarity. So this is the polarity of voltage VD1 and the current is ID1. The current in diode is same as the current through the source, flowing through the source and also the load resistor. So with this polarity of voltage, if we write KVL, VD1 is given by Vs minus Vo, and Vs is the source voltage minus VO. What is VO? VO is the voltage across the resistor, which is ID1 times R. And ID1 is 0 because we assume that diode is off, so no current is flowing in the circuit. So VD1, the voltage across the diode, becomes equal to Vs, which is actually greater than 0. That means the voltage across the diode is greater than 0. That contradicts the assumption of diode being off. It will become inconsistent. A diode cannot be off and block a positive voltage. So the diode should be on when the voltage is positive in this circuit. So D1 is on when Vs is greater than 0. And under such condition, what will be the output voltage? The output voltage will be simply equal to Vs, because the voltage across the diode VD1 can be neglected when it is on. This is true in most of the power electronic circuits, where the voltages are much larger than the drops that occur across diode. Diode drops hardly 1 or 2 volts, whereas Vs, in the most realistic case, Vs is an AC source. Usually we have 230 volts RMS voltage, so the peak voltage Vm itself is 325, which is much larger than the 1 or 2 volt drop. So our assumption of output voltage being equal to input voltage when the diode is on is valid. And how does the current look like? The current looks like, again, Vs by R, because of the same approximation. So the current waveform is shown in green color. We are looking at the first interval 0 to pi when the input voltage is positive. So when the input voltage is positive, output voltage is equal to the input voltage. So that is why this red color waveform and dotted blue color waveform overlap from 0 to pi, and the source current Is, which is also the diode current, which is also the resistor current through the resistor, because it's a series circuit. So that varies as shown in green color waveform. So it is also a sinusoid in this 0 to pi interval, and is proportional to the input voltage, and the voltage across the diode is 0 when it is on. What happens after pi? That means when the voltage becomes negative, the source voltage becomes negative. Since D1 was on from 0 to pi, let us assume that it continues to be on. So since we have assumed that the diode is on, we need to make sure that the current flowing through the diode is positive, because diode cannot carry negative current continuously. And so we need to look at ID1 to check the consistency of our assumption. So how do you get ID1 in this circuit? ID1 is simply Vs by R, because diode was on initially and we have assumed that it continues to be on. So the current to the diode is Vs by R, but Vs by R is less than 0. So diode current turns out to be negative if we assume it to be continuing to conduct. So the diode should turn off as soon as the voltage becomes negative. That means diode should turn off at pi. And when the diode is off, what is the output voltage? There is no current in the circuit. So ID1 times R, which is the output voltage, is 0. The source current is also 0. And what is the voltage across the diode? The voltage across the diode when it is off is same as the source voltage Vs, shown in the purple color waveform here. So the maximum voltage that needs to be blocked by the diode is Vm, and this is repetitive. It repeats in every line cycle, or if the frequency of input AC voltage is 50 Hz, this maximum voltage appears across the diode every 20 millisecond interval. Since we are interested in the DC value of the output voltage, we need to find its average value. The average value of output voltage, that the red color waveform shown here, which is denoted by VO average and also shown by a dotted red line here. VO average is equal to Vm by pi, and how do you get this? It is simply 1 by 2 pi integral 0 to pi Vm sin omega t. And how about the source current? Since it's a rectifier, we are always interested to look at the input current waveform, source current waveform, and output voltage waveform. Output voltage should ideally be a constant voltage, which is an ideal DC, but it turns out to be a sine wave with no negative half cycle. The negative half cycle becoming 0, so it is not close to an ideal DC waveform. And how about the input current? The input current also has the same waveform as shown in the green color. The current should ideally be a sinusoidal AC waveform, but in this case the source current is not even a perfect AC waveform as per our notion, because it has a finite average value. This is the case with almost all the single phase half wave rectifiers, so that is why they are very rarely used, but they are a good starting point to understand the fundamental principles of the operation of many rectifiers.